Good morning to all of you. I welcomes to all in the lecture series on quantum mechanics. Today we are going to discuss about another half portion of one-dimensional linear harmonic oscillator in quantum mechanics. In our last video or last class, we have been discussed in detail what is the physical significance of harmonic oscillator in quantum mechanics, how potential energy is going to be stored, and what is the nature of the potential energy curve, and from the eigenvalue equation, this is how it is in the form of Schrodinger equation, and how this differential equation is going to be transformed to another equation like this, and using equation number 7 we found the eigenvalues. In detail we have been discussed in our last video. So I suggest that before you have to watch today's video or this video, you go for that last video. Okay, so we found that the eigenvalues are h cross omega for the lowest energy state. Next excited state having the energy is 3 by 2 h cross omega, next 5 by 2 h cross omega, next 7 by 2 h cross omega, and from that we found that the spacing between the two energy levels is h cross omega. Okay, so at last we found that energy eigenvalues of a particle moving in a linear oscillation form an equispaced discrete energy level or spectrum. The energy levels are discrete. All the energy value are not accepted. See, here h cross omega is accepted for lower energy state. Okay, h cross omega by 2. Here I mistakenly written that h cross omega. You just correct it. You correct it. This one h cross omega by 2. H cross omega by 2. I mistakenly written over here, because if we have to put n is equal to 0, then it will be h cross omega by 2. You correct it. Okay, so for the lowest energy state having the energy is h cross omega by 2, and the next excited state having the energy 3 by 2 h cross omega. That means in between that the energy value is not acceptable for a particle or for a quantum particle which is oscillating in the dynamics of oscillation. That means the lowest energy state having the energy is half h cross omega, that means 0.5 h cross omega, and the next excited state having the energy 3 by 2 h cross omega, 3 by 2 h cross omega, or you can write 1.5 h cross omega. So in between that the energy values are not acceptable, means 1 h cross omega or 1.2 h cross omega. That means intermediate values are not acceptable. Okay, so up to this much we have been discussed in detail. So you go through that video before you have to watch today's video. Today we are going to discuss about Eigen Functions. Eigen function, that means if the particle having the energy or stationary energy value for ground state is this much, next excited state is this much, that means for these states have definite eigen functions. Only for that we can get the definite eigen values. So what are the eigen functions for these levels, that we are going to be find out today's lecture. So now we have to consider equation number 10 and substitute lambda value. Lambda, how much we found? We found lambda is equal to 2n plus 1. Now this 2n plus 1 I am going to be substitute in our main equation, that is equation number 10. This is your main equation, that is equation number 10. This is equation number 10 that what is a second order differential equation with having variable coefficient we found, and it is solved by the using the power series method, and here I am going to put lambda value. Okay, so acceptable value of lambda whatever we found. So acceptable value of lambda we found 2n plus 1. Now whenever we have to put in equation number 10, how much we can get, or the equation 10 will be modified as d square f, this is a function of y, dy square minus 2y df by dy plus 2n fy equal to 0. Let it is equation number 21. Okay, our last equation number, this one is 20, so hence it is 21, because as this topic is continuing, so here this is 21 equation number. This is well known Harmonic differential equation. This is very well known Harmonic differential equation. So now if it is Harmonic differential equation, now we are not going to be solve each and every step of the Harmonic polynomials etc., because we studied in detail in our last third semester. So here I am going to use directly the solutions of this equation, because as it is a Harmonic differential equation, then its solutions are A R E, this is A R E, are the Harmonic polynomials. Harmonic polynomials. So Harmonic polynomials are nothing but this one, that means h n y will be equal to minus 1 to the power n into e to the power y square d n e minus y square by dy square. So this will be the solution of this equation, because as it is Harmonic differential equation. Let it is equation number 22. So here I suggest to you one thing, that you just write carefully, because these are the subscripts. Here n is there, so many things are there, so you have to carefully write the note. Okay, otherwise the chances will be mistake will be more, because you are writing from the video. Okay, so now this equation 22, as it is Harmonic polynomial, so hence it has to be satisfied the recurrence relation, that is h n plus 2y equal to 2y h n plus 1y minus 2 n plus 1 h n y. Let it is equation number 23. Here these are the derivations, how it is the recurrence relation and how it will satisfy the recurrence relation, and all other things in detail we have been studied in our third semester. So here I am writing directly the results regarding Harmonic differential equation. So as this is the Harmonic polynomial or the solution of this differential equation, so hence this will be satisfy the recurrence relation will be this one, h n plus 2 and this one. Okay, this is one information, and also this this solution also will be obey the orthonormality condition, that is h n y h m y into e to the power minus y square dy is equal to 2 to the power n factorial into root over of pi delta nm. Let it is equation number 24. This is minus infinity to infinity. So these are the results whatever we can found or we found in our third semester for a Harmonic differential equation. So here we are just writing the properties of the Harmonic differential equation or results whatever we found at that time about Harmonic differential equation. So here, as it is a Harmonic differential equation, that is equation number 22, then it has to be that means its solution will be in the form of Harmonic polynomial, that will be this much, and this will be satisfy, that equation number 2 will be satisfy the recurrence relation, and also it will be satisfy this one, this solution also satisfy the orthonormality condition. So these are the so called results or properties whatever we found for the Harmonic differential equation, and here I written directly. Okay, because if we have to solve these three equations, it will be again so long question. So here, as we are concentrating to solve or to find out the eigen functions of our problem, one dimensional oscillation, so these are the results we are going to be use whatever we have been studied in our last semester or third semester, right? Now, hence eigen functions of harmonic oscillator are, they are expressed as psi ny equal to an. Here an is nothing but normalization constant hny into e to the power minus y square by 2 from equation number 9. You just check your equation number 9. Whatever we found, the generalized solution is fy e to the power minus y square by 2, and fy here is nothing but the so called Harmonic polynomial, that is hny. So instead of fy we have to consider hny. So hny I have been considered instead of fy, and an is a arbitrary constant or the so called normalization constant. Okay, so now psi nx, this is in the form of y. Okay, this is psi ny, an, hny. So if I am going to be modified to in the form of x, then I am going to be write y equal to alpha x, because these things we have been considered in equation number 5i. You can check 5i, equation number 5i, we consider that this one, see this one, we have been considered that this one, y equal to one constant into x. Okay, so this constant here we consider that this is alpha. Okay, so here if we are going to write instead of y, that is y equal to how much, that is m omega h cross root over into x, m omega by h cross root over 1 by 2 into x. So y square will be how much, m omega by h cross into x square, and here we have been considered that m omega by h cross is alpha. Okay, so in the form of x, this will be psi nx, an, hn, alpha x, y is nothing but considered as alpha x, and e to the power minus alpha square x square by 2. Okay, here alpha has been considered as this one, this is alpha square, this is alpha square, y square will be alpha square. So here y is considered as alpha into x, alpha is nothing but this one, m omega by h cross root over, here we considered that one. Okay, so this will be in the form of x. Here an is the normalization constant which can be determined by using normalization condition. So this is our wave function we found in the y form, and this is our in the x form. Okay, so now considering the normalization condition, so we know that the normalization condition is nothing but psi n star x into psi n x dx will be equal to 1. Then this is called the normalization condition. That will be the psi n value, psi n star and psi n value from here, from equation number 26. If we are going to be put, then it will be an mod square hn star, and this will be e to the power minus alpha square x square by 2. So it will be add up, then it will be e to the minus alpha square x square. We are going to get alpha square x square. So it will be hn star alpha x, hn alpha x into e to the power minus alpha square x square dx equal to 1. So just I discussed that y is considered as alpha x. So dy is equal to alpha dx. So put here in this equation we found an mod square minus infinity plus infinity hn y and hn star y hn y e to the power minus y square dy by alpha equal to 1. Okay, so it will be an mod square by alpha, this is nothing, an mod square by alpha minus infinity to plus infinity hn star y into hn y into e to the power minus y square dy is equal to 1. And this integration value, this integration value will be this much by using gamma function. How it will be, I am going to show you one or two n values. For one or two n values I am going to show you. Wait, so this will be equal to 1, so n mod square by alpha into 2 to the n factorial root over pi equal to 1. Let it from equation number 24, from equation number 24, because from equation number 24 we found this one, right? From equation number 24, because equation number 24 is told that orthogonality condition. So if it will be Hn and Hn orthogonality condition. Wait, this is I done a mistake. Here I done a simple mistake. Here Hn star, okay, Hn star y hmy e to the power minus y square dy e2 to the power n factorial root over of pi delta nm, which is nothing but called as orthonormality condition. Okay, so from this equation number 24, if delta, this is the Kronecker delta, if n equal to m, so delta nn will be equal to 1. So now by using equation number 24, this value will be how much? 2 to the power n factorial into root over. That will be 2 to the power n into n factorial into root over of pi. So root over pi is equal to 1, and an will be equal to alpha by 2 to the power n factorial root over pi to the power 1 by 2. Here a square, so 1 by 2. Now put this one in equation number 26. In 26, if we are going to be put, then the psi n x will be alpha by 2 to the power n into n factorial root over pi to whole to the power 1 by 2, or the so called root over into hn alpha x into e to the minus alpha square x square by 2. That is equation number 27. Here I put the value of an. We found the equation number 27, and here n equal to 0, 1, 2, 3 and so on. Using equation number 22, the value of hn we are going to found like this one. See, here equation number 22 is this one. First we have to put h equal to 0. H equal to 0 means minus 1 to the power 0 e to the power y square into d 0 e to the power minus y square by d is 0 e to the minus y square by dy 0. Okay, that means there is no derivative. No derivative means, so this will be e to the power y square into e to the power minus y square will be equal to 1, and this will be equal to 1. So h0 we are going to get 1. The value will be 1. h0y equal to 1. Likewise, if we are going to find out the h1 value, then the value we are going to get 2y. The value we are going to get 2y. Here you can see we are going to extract the value of h1y. h1y means the n equal to 1, so minus 1 to the power 1 e to the power y square. So this is the first, we are going to take the first derivative of this one. First derivative of this one, e to the power minus y square. That means minus 2y e to the power minus y square. Here minus plus 2y e to the power y square e to the power minus y square. So e to the power 0. So we found 2y. Likewise, we can found h2y, h3y. So likewise, if we are going to consider this equation for higher value of Hermite polynomial, then the values are, we are going to get, these are the values. So h1 we can found 2y, and or if we are going to consider y equal to alpha x, then it will be 2 alpha x. h2y we can found 4y square minus 2 or 4 alpha square x square minus 2, and h3 will be equal to 8 y cube minus 12y we found from this equation number 22. Now this value will be equal to this much. How it is, I am going to be show you by one or two taking the one or two values of n. See, by considering gamma function, okay, gamma function, we know that according to gamma function, carefully, no need to write these things, you just watch it and you can write in your rough. We know that gamma function is nothing but 0 to infinity t to the power n minus 1 into e to the power minus t dt is nothing but gamma n. And another gamma half, we know that root pi. Okay, now this value will be equal to this much. That we have to be cross check. Okay, first we have to take h0x. What is the value of h0x? 1. So here I am going to put, if h0x, then 1 into 1 will be 1 and e to the power minus y square dy, e to the power minus y square dy. So this is a even function. So even function means it will be written as 0 to infinity. Okay, so here we consider minus y square as t. So 2y dy equal to dt, and dy will be equal to dt by 2y, and y will be root over of t. And as this is the even function, it can be written as 2 into 0 to infinity e to the power minus 2 into dy. Instead of dy, I can write dt by 2 into root over of t, right? So it will be, see, this is 2 got cancel, t to the power 1 by 2. If it will go to the numerator, it will be t to the power minus 1 by 2 into e to the power minus t dt. So it can be written, this e to the power, t to the power minus 1 by 2 can be written in the form of t to the power 1 by 2 minus 1. Here I am writing to compare to the gamma function, means gamma function will be in the form, if it will, I am trying to put in this form, t to the power n minus 1 into e to the power minus t dt. So here t to the power n minus 1 into e to the power minus t dt. So this is transformed to gamma function, that is 0 to infinity also. So this will be, value is gamma n, this will be gamma n. So t to the power n minus 1 into e to the power minus t is gamma n. So here gamma n will be nothing but gamma half is equal to root pi. So now if we are comparing this value, that is 2 to the power 0, n equal to, we are going to take 0 na. So 2 to the power 0 equal to 1, 0 factorial 1, we found only root pi. So 2 to the power, for n equal to 0, 2 to the power 0, 0 factorial, root over of pi, we found root pi. So in this way we found root pi. Likewise we are going to take h1x equal to 2y. h1x equal to 2y means we are going to put here, this is hn star and hny. So hn star into hny will be how much? 2y into 2y, 4y square into e to the power minus y square dy. Okay, as it is both are even function, y square and e to the power something is even function, so this will be see 4 into 2, 0 to infinity y square e to the power minus y square dy. Okay, put t equal to y square, 2y dy equal to dt, dy equal to dt by 2 root 2, and you just put these values over here, then 4 into 2, 0 to infinity t into e to the power minus t into dt by 2 into root over of t. Okay, so it will be 4, here 2 and 2 got cancelled, 4, 0 to infinity t to the power 1 by 2, because here t to the power 1, here t to the power minus 1 by t to the power 1 by 2. So if it will move to numerator, it will be t to the power 1 by 2 into e to the minus t dt, and this 1 by 2 can be written in the form of 3 by 2 minus 1, and this is came into the picture of gamma function, right? T to the power n minus 1 into e to the minus t dt. So this will nothing but t gamma n. Gamma n means gamma 3 by 2. Gamma 3 by 2, we know that gamma n plus 1 is equal to n gamma n. This is also we know. Okay, so here 4 is there. So this 3 by 2 can be written as 1 by 2 plus 1. Okay, So 3 by 2 can be written as 1 by 2 plus 1. So n plus 1 is equal to n gamma n. So here n means 1 by 2 plus 1 means 1 by 2 gamma 1 by 2. So 2 got cancelled, it will be 2 root pi, right? 2 root pi. Now we have to cross check this value we are going to get from this or not. You put n is equal to 1, n is equal to 1 means this will be 1, this will be 2, and this will be 1, and this will be root pi. So 2 root pi, we can get 2 root pi. In this way we got also 2 pi. The cross check is our success. And now we are going to consider h2x. Okay, h2x. See, I am not going to be say to you that you have to write in your note. This is only for your confirmation. You can write in your rough, or you can for your practice purposes. See, h2x. Now we are going to consider h2x, which is the value is 4y square minus 2. So if we are going to consider the 2 to the power n factorial and root pi, then by substituting the value of 2, it will be 2 to the 4, 2 factorial, root over pi, it will be 8 pi. So in this way, we are going to get 8 pi or not, that we have to cross check. Okay. So here, what is the things, that is hn star into hn into e to the power y square. Okay, that is the things here. Hn star hn into e to the power minus y square dy. So here h2x is equal to 4y square minus 2. So this will be h2 star h2. That means this square 4y square minus 2 whole square into e to the minus y square dy. So you just consider as a plus b square. This is a plus b square, means it will be 16y to the 4 plus 4 minus 16y square into e to the minus y square dy. You can multiply this with each term. You can get 16y to the 4 e to the minus y square dy plus 4 minus infinity to infinity e to the minus y square dy minus 16 minus infinity to infinity y square into e to the minus y square dy. Okay, here I am doing only for your confirmation purposes. These things should not be written in the exam for this question point of view. This is your only for your confirmation and practice. Okay, so here this function is even function, so it can be written as 2 into 0 to pi 0 to infinity y to the power 4 e to the minus y square dy, and it can be written as 2 into, that means 8 into 0 to infinity e to the minus y square dy, and here also it can be written as 2 into 0 to infinity. It will be 16 into 2 0 to infinity y square into e to the power minus y square dy. Okay, now put y square as t, 2y dy equal to t, same thing, dy equal to t by 2 root over of t. So this will be, see here 2 into 16 0 to infinity. Here I am going to put instead of y square as t, so it will be t to t square into e to the minus t dt by 2 into root over of t plus 8 into 0 to infinity. I just substituted instead of y square as t here. Okay, so here 2 got cancelled, 16 into 0 to infinity, it will be t to the power 1 by 2. If it will move to this one up, then it will be t to the 3 by 2, and likewise this t to the 1 by 2, if it will move to off, then it will t to the minus 1 by 2 e to the minus t dt, 16. Here 2 got 2 and 32, it will be 16 t to the 2 e to the minus t dt. So this t to the power 3 by 2 can be written as n minus 2, that means 5 by 2 minus 1, and this minus 1 by 2 can be written as n minus 1 form, that will be 1 by 2 minus 1. This 1 by 2 can be written in the form of 3 by 2 minus 1 by comparing or to transform this in the form of gamma function. Okay, so this is 16, and this will be nothing but gamma 5 by 2, this will be nothing but gamma 1 by 2, this is nothing but gamma 3 by 2. So gamma 5 by 2 can be written as 3 by 2 plus 1, and it can be 3 by 2 into gamma 3 by 2. Again 3 by 2 can be written as 1 by 2 plus 1, or 16 into 3 by 2 into 1 by 2 into gamma half will be root pi. Okay, and here gamma half will be root pi, so 4 root pi, 4 root pi, 4 root pi. Here gamma 3 by 2 can be written as 1 by 2 plus 1 or 1 by 2 gamma 1 by 2. This will be 8 root pi, and we are going to get the 8 pi. So in this way also we got the 8 pi. Here I cross checked the value of this one. This one is true, means this will be, in general we can write this one, or you can consider higher value of Hermitian Hermite polynomials, and you can found the same. So we found the generalized wave equation or generalized eigen function is this one, equation number 27. Okay, now for n is equal to 1, for n is equal to 1, here you can write somewhat, I not written, for n is equal to 0, sorry, for n is equal to 0, psi 0, here we just evaluated the few wave functions from the general eigen function. This is your general eigen function of the harmonic oscillator. So now we are going to put n is equal to 0, 1, 2, 3. We are going to get first energy states eigen function, and if you are going to put 1, then it will be eigen function of the second excited state, like that. So for n is equal to 0, this will be this much. You pause the video and you have to write down. Okay, in the form of psi x I am writing, in the form of psi x. Okay, psi x I am writing. That means this value you can consider, this value, these values you are going to consider for this one. Okay, so by considering 27 and these values, for n is equal to 0 we can found this one, and for n is equal to 1, psi 1 will be this one. You just pause the video and you have to write, and you can also consider the equation number 26. The eigen functions are from equation number, what is 27, sorry, 27, equation number 27. So this will be the psi 1 x, that means second excited state eigen function. This will be the, for n is equal to 2, for n equal to 2, and this is for n is equal to 3. You pause the video and write down the values. Psi 2 will be this much, psi 3 is this much. Here I just substituted the hn alpha x value. Hn alpha x, h1 alpha x is equal to 2 alpha x, h2 alpha x 4 alpha square x square minus 2, 4 alpha square x square minus 2, and 8 alpha q x cube minus 12 alpha x. Only substituted, and we found here only 4 energy states eigen functions we have been just evaluated. You can in this way you can also found higher states eigen functions. So here psi 0, psi 1, psi 2 and psi 3 represents 4 lowest eigen functions or acceptable wave functions of harmonic oscillator. Okay, and here we found one thing, that hn minus x is equal to hx when n is even, but hn minus x is equal to minus psi n minus x is equal to psi n x, and psi n minus x minus psi n x when n is odd. You just check it. Suppose you have to consider the psi, this is odd, so minus, if you are going to put this is here, minus means it will be considered as minus, xq means minus, so it will the value of minus psi n x, or psi 3 minus x will be minus psi 3x. But if we are going to consider psi 2x, psi 2 minus x will be psi 2x, because it is in the form of square. Okay, So eigen functions of harmonic oscillator are definite parity, have the definite parity. Okay, that means if we are going to consider that is minus x, it changes to minus of that function for in the case of odd, but in case of even it is not going to be changed. Now probability density. So if we have for a state's eigen function, suppose we have eigen functions of a state that is psi, then probability density of that state will be psi star and psi. This will be the probability density, or we can say that psi mod square. So in general, the probability density in nth energy state is rho n x is equal to psi n star x into psi n x, or equal to psi n x mod square. So this is the probability density expression. Now graphical representation of eigen functions and probability density. Next page. Okay. Here again I am going to suggest that you just pause the video and you have to write down the notes, because it is essential for your exam purposes. Okay. So this is the graph, or this is the figure, represents the psi n x for different n. So from the, if we are going to plot, suppose this is our psi 0x, psi 1x is this one, psi 2x is this one. Okay, this is in the form of e to the power x square, right? E to the power x square. E to the power x square means if we are going to put e to the power x square, then the curve will be only e to the power x square. Only e to the power x square is there. So if we are going to draw the curve, then this will be like this, right? This will be like this, along positive x-axis direction, along negative x-axis direction. So but now if we are going to consider fast state or zero or we can say that ground state, this is in the form of minus x square form. Okay, and it is a constant. So this is indicates that this is the so-called Gaussian wave function. I told to you in our previous video, whenever I discuss, we have been discussed about the Gaussian wave packet, spreading of Gaussian wave packet. I told that whenever you found e to the power x square or e to the power minus x square, this is nothing but represents a Gaussian wave function. This represents a Gaussian wave function. So here this one is the Gaussian wave function, means it will be symmetric about both positive and negative x-axis. So this is the wave function representation of the ground state of harmonic oscillator. Now what is this this curve? This curve represents your potential energy as we are moving from origin or from the center to outside. The potential energy vary like this. The potential energy is varying like this. Okay. So this is the curve of potential energy, and this curve is the wave function of fast excited state. Fast excited state. I told that is the ground state. For n is equal to 0, ground state. If we have to consider n is equal to 2, n is equal to 1, then the wave function will be this much, and the graph of this, if we are going to draw, then the graph will be this much, like this. Okay. Likewise, for n equal to, the graph will like this. For n equal to 3, the graph will be like this. Okay. Here one thing we can consider, or we can found that, see, at x is equal to here, you just you can mark over here, at x is equal to, suppose up to this much distance, at x is equal to L, at this point. For x is equal to L, potential is this much. That means maximum potential will be this much. Okay, maximum potential will be this much. That means the corresponding restoring force is that much, that the particle could not be moved beyond of that potential energy or the potential. That means here I can show the example that suppose I am going to be displaced this particle from here to here. That means whenever I displaced the here to here, how much I have been work done, that much energy has been stored in this. So if we have to just give a energy of a certain energy we are going to give, then it has to move up to a certain distance. Up to a certain distance means how much work done we have been we are going to be do at the time of doing displacement from one place to another place. Okay, beyond of that it could not be moved. So potential energy, how much it has to be stored, only that much distance it can be moved. Beyond that it could not be moved. Okay, but in quantum mechanics, beyond that also wave function somewhat exists. See, wave function exists or the particle exists in between this to this potential, classically, but quantum mechanically it can also exist beyond that and beyond that. That means up to this much maximum force is there and it is trying to drag to its original position classically. But quantum mechanically, so if it will be so, then classically we are not going to found the particle beyond that limit, beyond that distance. Particle could not be exist. But quantum mechanically, the wave function will be there, means particle also can be found beyond that potential. Okay, so the wave function, all the wave function from all the wave functions for all the states, we can found beyond that potential there is existence of this particle. There is wave function is exist, wave function is exist, wave function is exist. Okay, this is most important thing. This is most important thing in your oscillator, that beyond that potential we can also found the information regarding particle. And this is your psi n for n equal to 0, this will be psi 0 and this will be psi 1, like that we are already discussed. So from the this figure what we got, that here I written somewhat, you just I'm reading, you just watch. The ground state wave function psi 0 has no nodes. Yes, here one thing you can observe from this graph, that node means there is no zero for this wave function psi 0. Psi 0, in between this boundary there is no zero value, okay. But in case of n equal to 1 there is one node. For n equal to 2 there is two nodes is there. Okay, for n equal to 3 there is 3 nodes. Okay, 3 nodes are there, means here the particle presence is 0. Particle presence is minimum, we can say the presence of particle is minimum, or probability density at here and here for this state is very minimum, and for this state here is minimum, means we can say that there is no probability of finding the particle in this n equal to 3 here and here. These 3 places we are not going to found any type of probability of finding the particle. Okay, likewise for n equal to these 2 places, for n is equal to 1 this place only, but n is equal to 0 there is no place. All over the boundary in between 2 boundaries we are going to get the probability of finding the particle, but maximum is at here. So here psi 0 has one node, it is a Gaussian wave function what I discussed, and the fast excited state psi 1 has one node, psi 0 has no node, psi 1 has one node, second excited state psi 2 has 2 nodes. In general, wave function of nth state has n nodes. Okay, now the probability distribution for the first 4 states. Here this is the representation of the probability distribution of corresponding wave function. So probability distribution will be always in probability, that means positive. So here it is a positive and this will be negative. This will be the so called, suppose your psi imaginary part, this is the real part, but we know that the probability density will be always positive, and this will be like this. So this negative will be in the representation of positive. So all the negative values will be represented as the so called psi mod square, that means this one. Okay, so the probability distribution for the first 4 states are represented in figure 4. This is figure 4. You just pause the video and carefully draw the figure. First I have to explain, then you have to draw. First you watch, then you have to draw. Something is there. So the intersections of probability curves with the potential curve gives the classical limit of the oscillation. That means intersection of the probability distribution. See, these are the intersections. Means at the boundary there is the intersections with potential curve Vx. This is your potential curve. So intersection means beyond the potential we are not going to get, we should not be found any type of particle. Okay, because this is the limit of the maximum force. So beyond that we should not be get the particle in the classical case. So but in quantum mechanics there is the probability. So only for that it is written a classical limit of the oscillation. Thus there is a finite probability of observing the particle outside the classical limit of the oscillation, what we discussed. For even function, rho x is maximum at x is equal to 0. For odd function, from this graph what we are going to find, rho x is maximum at x is equal to 0, and for odd function rho x is equal to 0 at x is equal to 0. See, for even function psi x is maximum. For even n is equal to 0, rho x, probability density is maximum. For n is equal to 0 it is maximum. For n equal to 2 it will be maximum. But odd, for odd, n value of odd, or for odd function, that means for n equal to 3 at x is equal to 0 is minimum. For n equal to 1, the x is equal to your probability density will be 0 at x is equal to 0. So this is all about your eigen functions and probability distributions of linear harmonic oscillator. And another point we are going to be discuss over here, you just watch that 0 point energy. The 0 point energy, this is most important question for the exam point of view. Always in the exam 2 marks questions is asked by that what is the meaning of 0 point energy of linear harmonic oscillator. The 0 point energy is defined as the particle in the oscillator well. The particle in the oscillator well. Oscillator well means it is oscillating like this. So up to this much distance it is moved along right hand side, and like this means it is oscillating. Or we can say it is in the potential it is oscillating, or we can say potential well, oscillator well. So particle in the oscillator well cannot be rest at the equilibrium position. That means at n equal to 0, E0 has the value of h cross by 2. Already we have been found in the in the eigen value. We found E0 is equal to, there is a value. That means it is telling that at equilibrium position, that is minimum energy state. But the minimum energy state has a definite value. So it is told that 0 point energy told that the 0 point energy is defined as the particle in the oscillator well cannot be rest at equilibrium position. So if we are going to say that the equilibrium position, the equilibrium position means one type of steady state. But in case of in case of your quantum mechanical harmonic oscillator, equilibrium position means it is not called as the rest. I am going to say you that this is the hydrogen atom, this is the nucleus, and the electron will be maximum probability going to be found at Bohr's radius, that is A0. It will be the maximum probability density. But at the minimum energy state itself, minimum energy state of the electron, this electron also fluctuate its along this way. Means it will be not at a steady state. if we are going to say the classical particle is at equilibrium state or minimum energy state, that not mean, again I am repeat, that is not meaning that it is at rest. Okay, it is in the oscillation, minimum oscillation or minimum fluctuation. So unlike in, but in case of classical, equilibrium position means there is no equilibrium position means this one. This is called the equilibrium position. If it is disturbing, then it is non-equilibrium position. But in case of quantum mechanical case, this is cannot be at rest. Okay, so unlike classical mechanics, quantum systems constantly fluctuates in their lowest energy state, which follows the Heisenberg uncertainty principle. So if quantum mechanics is in the dynamic states, then its corresponding del x and del px at a particular time and particular place, there will be a uncertainty, that will be follow the uncertainty, because if we are going to predict its uncertainty of del x, there uncertainty of momentum also came into the picture, and this will be equal to h cross by 2, approximately h cross by 2. So here we conclude that at the lowest energy state or at the equilibrium position, or for the equilibrium position, the quantum oscillator not in the rest, it obeys the Heisenberg uncertainty principle. There is a problem we can solve, or we can solve that one, that we are going to found at the lowest energy state. This is the lowest energy state, we are going to get the h cross by 2, means it will obey the Heisenberg uncertainty principle. How it will be? Here I written a question, but this is one type of proof, that we can prove that at lowest energy state it will follow the uncertainty principle, means there will be a dynamics. If this is true, that means there will be a dynamics. Okay, so these things we are going to be discuss this how it will be follow the Heisenberg uncertainty principle in our next class. And also in the next class we are going to discuss about classical probability density and quantum mechanical probability density of linear harmonic oscillator. Yes, one thing I forgot to say to you, that see, this probability density at the corner will be increase, this will be increase, and this will be decrease. Okay, this will be decrease. And if we are going to increase the n value, it will be like this. This at the corner will be maximum, and at in intermediate it will be minimum, and it will be maximum, like that. That things we are going to be discuss in our next video, in this probability density of quantum mechanics probability density, classical and quantum mechanical probability density. So thank you so much for watching this video. I suggest that you go for this video, carefully write the notes, because it is useful for your exam purposes. And if any doubt, you can ask me. Okay.